Good morning and afternoon, everyone, and welcome to our project presentation. Today, we present our project for the course MMK 21103, Computer Aided Engineering under the guide of TS Dr. Muhammad Iqbal bin Ishaq. Our project is titled Design Improvement and Analysis of a Wheelchair Footrest. In this presentation, we will share how we improve the existing footrest design using CAE tools to make it stronger, safer, and more comfortable for user. Let's begin with the background of our project.
Hi, my name is Nura Azri binti Azri. My matric number is 241352284. I, as a student 1, gonna present intro, objective, design improvement 1, and also change of material.
Hi, my name is Nur Naziha binti Muhammad Zaki. I am a student number 2 in this group. I will explain about methodology that used in this project. All about improvement 2 and thermal analysis.
Hi, Assalamualaikum. My name is Nur Fatiha and I represent as member number 3 who will be presenting about design improvement 3 and topology optimization.
So, for introduction, wheelchair footrests are important structural component because they must safely support the user weight during everyday activities. If the design is not strong enough, it may experience excessive stress and less deformation or even structural failure, which can affect both user safety and comfort. To evaluate the structural performance before manufacturing, this project we use computer aided engineering, or we call it CAE, through NC Workbench. This simulation allows us to predict important performance indicators such as equivalent von Mises stress, total deformation, and the factor of safety, or we call it FOS. It helping us to identify potential weakness while reducing the need for costly physical prototypes. Therefore, the aim of this project is to analyze the structural performance of wheelchair elevating footrest, identify the critical stress regions, and propose design improvement to enhance its strength, safety, and overall structure performance. Next, I will explain the objective of this project. The first objective is to develop a 3D model of the wheelchair elevating footrest using CATIA and perform structural analysis using NC's Workbench. The second objective is to identify the critical component that experience the highest stress and total deformation under the applied loading condition. The third objective is to propose and evaluate 3 design improvement. The performance of each design is compared based of 3 key parameters, which are stress, total deformation, and factor of safety. Finally, the best design is selected and it performed is further evaluated by considering different material types, thermal condition, and topology optimization to determine the most suitable design for the wheelchair footrest. As you guys can see, the workflow of this project is shown on the right. The process begins with 3D modeling in CATIA, followed by structure simulation in NC's Workbench, and after that, based on the analysis result, several design improvements are proposed and compared. And lastly, the best performing design is selected for further evaluation.
Next, I will explain the methodology used in this project. First, the wheelchair elevating footrest was designed as a 3D model using CATIA. Then the model was imported to NC's workbench for simulation. Next, the material property were assigned following by meshing to divide the model into many small elements for more accurate analysis. After that, all contact between the components was set as a bonded, which means every part was assumed to be firmly connected without any movement between them. Then, the boundary condition were applied by fixing the main tube while a 150 Newton load was applied on the footrest plate to represent the user's leg force. After completing the setup, static structural analysis was carried out to obtain the equivalent stress, total deformation, and a factor of safety. Finally, the result of the original design and the three improved design were compared to determine which is the best design.
For design improvement 1, the thickness of the main upper tube was increased by 1 mm. This modification was made because the original analysis showed that this area experienced the highest stress concentration. Increasing the thickness helped improve the load carrying capacity, reduce stress concentration, and enhance the structural strength of the wheelchair footrest. The simulation result will be compared with the original design in the following slide. This slide compares the original design with design improvement 1 based on the NC simulation result. As shown in the counter plot and the comparison table, the original design record a maximum stress of 191.02 MPa. After increasing the thickness of the main upper tube by 1 mm, the maximum stress decreased to 170.21 MPa, representing a 38.64% reduction. Similar to the maximum total deformation, it decreased from 6.9271 mm to 4.0265 mm, which is a 39.28% improvement, indicating that the structure becomes stiffer and more stable under the applied load. In addition, the factor of safety increased from 1.1255 to 1.8343, an improvement of 62.97%, meaning the modified design has a much larger safety margin. Overall, increasing the thickness of the main upper tube successfully reduced stress and deformation while improving the factor of safety, making design improvement 1 structurally stronger and safe than the original design.
Now, I will explain design improvement 2. In this design, structural ribs, also known as a gusset, were added between the upper handle and the main vertical tube. So it will be like triangle. This modification was made because the original design showed height bending stress at the handle joint. The gusset increased the stiffness of the structure and provide an additional pads for the load to travel. Instead of concentration the force in one small area, the load is distributed more evenly throughout the structure. As a result, stress concentration is reduced, making the joint stronger and more stable. So, after adding the structural ribs, the structural performance improved compared to the original design. The maximum equivalent stress decreased from 191.02 MPa to 145.66 MPa, which is reduction of 23.75%. This happened because the gusset distribute the applied load over a larger area, reducing stress concentration at the joint. Next, the total deformation decreased from 6.9 to 71 mm to 3.378 mm, which is reduction of 51.53%. This shows the structure becomes stiffer and bend less under the same loading condition. Lastly, for the safety increased from 1.1255 to 1.476, which is improvement of 31.14%. A higher factor of safety means the design has a greater safety margin before failure. Overall, the design improvement tool successfully improved the structural strength and stiffness of the wheelchair footrest. This improvement shows that the adding reinforcement can effectively increase stiffness without changing the overall function of the design.
The improved design replaced the original single band upper tube with a dual tube handlebar and an additional U-shaped support frame. This modification distributes the applied load more evenly, reducing stress concentration at the band section while increasing the overall stiffness and bending resistance of the structure. The dual tube configuration also improved stability against bending and torsion, resulting in a higher factor of safety and a stronger and safer wheelchair frame. Let's look at the performance comparison between the original design and design improvement tree, which focus on geometric and structural modification. Based on the FEA result, the equivalent bond massive stress decreased significantly from 191.02 MPa to 115.16 MPa, representing a 39.71% reduction, which means the stress concentration was effectively minimized. The maximum total deformation also decreased from 9.93 mm to 2.37 mm, giving a 65.72% improvement in structural stiffness. In addition, the factor of safety increased from 1.1255 to 1.8669, an improvement of 65.87%, indicating a much safer and more reliable design. As shown in the stress contour plot, the critical stress concentration near the lower junction was successfully redistributed.
In this stage, the material was changed from stainless steel T04 to titanium grade 5 while maintaining the same design and loading conditions. Titanium grade 5 was selected because it has a higher strength to weight ratio, excellent corrosion resistance, and good mechanical performance. After the material change, the maximum stress increased slightly from 115.16 MPa to 116.64 MPa, which is only a 1.29% increase. This shows that the stress distribution remained almost the same. Next, the total deformation increased from 2.3743 mm to 3.9422 mm, an increase of 66.04%. This is because titanium grade 5 have a lower young modulus than stainless steel 304, making it less stiff and allowing more deformation under the same load. However, the factor of safety increased significantly from 1.8669 to 7.1157, which is an improvement of 281.15%. This means the design have a much larger safety margin and it can withstand the applied load more safely. Overall, titanium grade 5 is the better material because it provides a much higher factor of safety while also being lighter, making it suitable for the wheelchair footrest.
After selecting the best design from phase A, thermal analysis was carried out. Besides the mechanical load of 150 Newton, a thermal load was also applied to study how temperature affects the wheelchair footrest. This analysis represents situation where the footrest is exposed to higher temperature during outdoor use or different environmental conditions. This purpose is to determine whether the temperature change if affect the stress, deformation and overall structural safety. From the result, the equivalent stress increased from 115.16 megapascal to 228.16.61 megapascal, which is increased 98.51%. The total deformation also increased from 2.3743 mm to 2.8923 mm or 21.82%. At the same time, the factor of safety decreased from 1.8669 to 1.0936, which is a reduction of 41.42%. This means the structure become much closer to its failure limit. Overall, the thermal load reduced the structural safety even though the geometry of the design remained the same. This happened because the material naturally expands when the temperature increases. But in this model, the main tube is fixed and cannot expand freely because the thermal expansion is restricted. Thermal stress is generated inside the structure. This thermal stress is combined with stress caused by the mechanical load of 150 newtons. As a result, the equivalent stress and total deformation become higher while the factor of safety become lower, which is not safe. According to the thermal stress equation, when the temperature increases and the material cannot expand freely, thermal stress develops inside the structure. This explains why temperature has a significant effect on the structural performance of the wheelchair footrest.
To push the design even further, we isolated a critical connecting component for optimization. The objective of this topology optimization was to create a lighter and more efficient component without compromising its structural performance. An 80% material retention target was applied, meaning only the material essential for carrying the load was preserved. The optimization removed non-load bearing material from low stress regions while maintaining the primary load part to ensure the component could still withstand the applied loading. As a result, the optimized design achieved a reduction in weight while preserving its structural integrity, making it more suitable for final implementation. Finally, we evaluated the performance of the assembly after applying the topology optimized design using design improvement 3 as the baseline. The equivalent buoyant master stress increased slightly from 115.16 MPa to 126.88 MPa, which is a 10.18% increase, but it remains within the material's safe operating limit. At the same time, the total deformation decreased from 2.37 mm to 2.07 mm, representing a 12.61% improvement in stiffness. Although the factor of safety decreased slightly from 1.8669 to 1.6945, a 9.23% reduction, it remained above the acceptable safety limit. Overall, the topology optimization produced a lighter and more efficient design while maintaining satisfactory structural performance. In conclusion, this project successfully improved the structural performance of the wheelchair footrest using CATIA and ANSYS. Design Improvement 3 showed the best overall performance by reducing stress and deformation while increasing the factor of safety. The material study showed that titanium grade 5 had the highest safety factor, while the thermal analysis increased stress and reduced structural safety. Overall, CAE simulation is an effective method to evaluate and improve the design before manufacturing. That's all from us. Thank you.